Look closely at any propeller, a plane, a boat, even a drone, and you'll notice something odd. The blade isn't flat. It twists along its length like someone grabbed both ends and turned them in opposite directions before it hardened in place. It looks like a manufacturing defect. It isn't. That twist is doing something you'd never guess just by looking at it. And the reason comes down to a fact most people have never stopped to consider. Different parts of the same spinning blade are moving at wildly different speeds, all at the same time. Here's the part that sounds impossible until you do the math. Take an ordinary small aircraft, a Cessna 172, one of the most common training planes in the world, spinning its propeller at a normal cruising speed. The tip of that propeller blade is moving at roughly 558 miles an hour. That's not a typo, and it's not an unusually fast plane. It's a small, slow, everyday aircraft. Now measure the same blade just 10 inches out from the centre, near where it attaches to the engine. That part of the blade is moving at only 149 miles an hour. Same blade, same rotation, same single moment in time. A 409 mile an hour difference between one end and the other. Why would that even be true? Because the tip has to travel a much bigger circle than the root does every single time the propeller spins around once. And it has to cover that bigger circle in the exact same fraction of a second as the root covers its much smaller one. Go further out, cover more distance in the same amount of time. That only means one thing. You're moving faster. Now here's where it actually matters. A propeller blade works the same basic way a wing does. It pushes air to generate force, and how much force it generates depends heavily on the angle it meets that air at. If every section of the blade were angled exactly the same way, the fast-moving tip and the slow-moving root would be meeting the air completely differently, purely because of how fast each one happens to be travelling through it. Left uncorrected, that mismatch doesn't just waste power. Parts of the blade could end up fighting each other. One section generating useful thrust, while another section, at the wrong angle for its speed, generates drag instead or barely helps at all. You'd have a propeller working against parts of itself. So engineers gave every section of the blade a slightly different angle, steep near the root, where the blade is moving slowly and needs to bite into more air to keep up, and progressively flatter as you move toward the tip, where the blade is already slicing through air so fast that the same steep angle would be wildly excessive. Twist the blade correctly, and every section, despite moving at a completely different speed than its neighbour, ends up meeting the air at close to the same effective angle. The whole blade starts pulling its weight instead of just the fastest moving part of it. That twist you notice, the one that looks almost like a mistake, it's the propeller correcting for the fact that it's not really one object moving at one speed. It's dozens of different points, all attached to each other, all moving at their own individual speed, all needing their own individual answer to the exact same question. What angle do I need to be at right now, given how fast I'm actually going? You'd think that's the whole story. It isn't, because this exact same rule applies somewhere you'd probably never think to look. Look at a helicopter. Its rotor blades are twisted too, for the identical underlying reason. The tip of a helicopter rotor blade travels dramatically faster than the root, for the exact same geometric reason a propeller does, and without a twist, the same imbalance would set in. Too much lift near the fast-moving tip, too little near the slow-moving root, the blade fighting itself instead of working as one piece. But a helicopter rotor has to do something a fixed propeller never has to deal with. A propeller on a cruising plane sees roughly the same conditions every time it spins around. The same airflow, the same angle over and over. A helicopter rotor doesn't get that luxury. As the helicopter moves forward, one side of the spinning rotor disc is always moving in the same direction as the aircraft, adding its rotational speed to the helicopter's forward speed. The opposite side of the disc is moving against the aircraft's direction, subtracting speed instead of adding it. That means a single rotor blade experiences a completely different airspeed on one side of its rotation than it does half a second later on the other side. A second layer of speed variation stacked directly on top of the tip versus root problem the blade already has to deal with. To manage that, most helicopters don't just rely on a fixed twist baked into the blade. They actively change the blade's pitch, its angle, continuously, moment by moment, as it spins, increasing it on the side moving against the aircraft and decreasing it on the side moving with it. It's the same underlying idea as propeller twist, solving the same root problem, except a helicopter has to keep solving it in real time, thousands of times a minute, just to stay level in the air. There's a limit to how far any of this can be pushed, and it's the reason propeller blades can only get so long before engineers have to stop. As a blade's tip speed climbs, it eventually approaches the speed of sound itself. On some aircraft, tip speeds reach Mach 0.75 or higher, 3/4 of the way to breaking the sound barrier on a blade that never leaves the vicinity of the engine. Past a certain point, no amount of clever twisting saves you. The air itself starts behaving differently near the speed of sound, efficiency collapses, and noise increases dramatically, which is exactly why propellers on the fastest aircraft eventually gave way to jet engines with no external blades exposed to open air at all. So, the next time you see a propeller on a plane taxiing to the runway, a boat idling at a dock, even a desk fan, look for the twist. Or better yet, watch a helicopter lift off and picture what's actually happening inside those rotor blades. Not one object moving at one speed, but dozens of points along a single blade, each one solving its own version of the exact same equation over and over every single time it comes back around.